Hello, welcome back. In this segment, I wanted to explain how to compute the GCD of two numbers if we know the prime factors. Let's say for 336 as an example, we can read it as 2 power 4 times 3 times 7. 2, 3, 7 are all prime numbers, of course. So similarly, 2156 can be written as 2 power 2 times 7 power 2 times 11. Now the question is, how can we compute the greatest common divisor for these two numbers? Okay, it turned out that you can just look at the common numbers. For example, 2 is a common number that is present here and here. Select just the minimum power. The minimum power is 2, right? Here it's 2 and here is 4. The minimum is 2. And now look at 3. 3 is only present here, but it's not here, so we can ignore it, meaning you can imagine there was 3 power 0 here, right? And here is 3 power 1. So you're going to only select the minimum, which is 3 power 0, which is nothing but 1. And look at next number is 7. It's 7 power 1 and 7 power 2 here. So that means you will select the minimum power, which is 7. And we have 11 here. That means we should put 11 power 0 here as well, which means the minimum is 11 power 0. Okay. You have to look at the 2. For 2, I need to take the minimum of 4 and 2, which is 2, right? So the answer is 4 into 1 into 7 into 1, which is 28. Okay. But the question now is, why am I selecting only the minimum power, right? What is the reason? I mean, it might be correct answer for this particular example, but what is the reason that minimum power is always true for all possible integers a and b? Okay, what is the reason that I need to select the minimum power for each of the prime factor that you're seeing here? So we can now prove this general theorem. We understand the basic example here, and we can prove a general theorem. So let's say you have a number a, right, which is made of some prime factors, right? Let's say p1 power a1, p2 power a2, right? And so on, and so on. And say pn power an, right? Pn power an. These are the n prime factors for number a. Okay. And let's say b is another number which also has prime factors. We can read it as, say, p1 power b1, p2 power b2, and so on, pn power pn. You may wonder why I'm using the same p notations here and p here, right? What is the reason that I'm using the same prime? If the primes are not occurring, you can always add them and put a power to the power 0. Therefore, there is no problem in selecting the same n primes here and the same n primes here. Okay. Anyway, so we have two numbers a and b. Now the question is, what is the GCD of a and b? So we need to prove that the GCD of a and b is a number d, right? Which is GCD of a and b. Has an interesting structure. The structure is nothing but p1 power d1, p2 power d2, and so on, pn power dn, where these di's that you're seeing on the superscript must satisfy this property that di is nothing but minimum of ai and bi. Okay. That's the reason why in the example I was selecting the small power, because I'm computing the minimum of the powers, corresponding powers. Okay. We need to prove that the GCD of a and b is a number d which has this structure. Okay. So we can easily prove that. Let's say, let me start the proof now. Let's say d is equal to p1 power d1, p2 power d2, pn power dn, and dA is equal to min of a comma bi, right? What is the definition of minimum, right? The definition of minimum says dA must be less than or equal to ai, and di is also less than or equal to bi. That is the definition of minimum, right? Less than or equal to bi. Okay. Now, we can right away use the previous proposition that we proved in the previous segment, that any number that divides A, right, must have the structure P1 power D1, P2 power D2, and so on. Do we have the same structure here? Yes, we do have the same structure, where each of the exponents you see here satisfy the property that it is less than the corresponding exponent. Okay, which means just applying the previous proposition we proved on the previous segment, that this particular D will divide A. Okay. D divides A is established just using the previous segment. Similarly, D divides B can also be established because DI is also less than or equal to BI. So D is a number that divides both A and B, which is one of the first conditions for claiming that D is a GCD. In order to say D is a GCD of A and B, we need to show D divides A, D divides B. That's the first part. We are done. Okay, the next part is to show that if there exists any other divisor for A and B, that divisor C, let's call it C, we have to prove C is smaller than or equal to D. That means D will be the greatest number, right? That's what we need to prove. Okay. To sum up, all we proved so far is that if we know D is B1, P1 power D1, P2 power D2, Pn power Dn, where Di is same as minimum of A and Bi, then D will divide A, D will divide B. So we established that part. All we need to do is to show that D is the greatest common divisor of A and B. That means any other divisor of A and B is smaller than or equal to D. That's what we need to prove. Okay, let's do that part now. All I'm going to do is, assuming there exists a C, right, that divides A and B. Okay, so let's assume there is a C which divides both A and B. Okay. What can we say about the structure of C? From the previous proposition, we know that C must satisfy this property that it must be of the form some P1 power, whatever you want to call it. Let's say P1 power C1, P2 power C2, and so on, all the way until Pn power Cn. This is just coming from the previous proposition. What can we say about the C's though? All these C's, the Ci's in general, must be less than or equal to AI, and Ci is also less than or equal to Bi. Okay, otherwise we cannot claim that C divides A and C divides B. Okay, so if Ci is less than or equal to AI and Ci is less than or equal to Bi, that means Ci will be less than or equal to the minimum of AI and Bi. Why? Because minimum of AI, Bi can be either AI or Bi, right? That's the reason why I say Ci has to be less than or equal to minimum of AI and Bi, which is nothing but Di, right? Di is, how did we define Di? Di is nothing but minimum of AI in Bi, which means Ci is less than or equal to Di. What have we established so far? We proved that the exponent power of each of the primes, right? P1 power C1, P2 power C2, all of these exponents that you're seeing on the prime factors of C are smaller than or equal to all the Di's that we see on the prime factors of D, which means C has to be smaller than D, because you're comparing P1, if the power is smaller than D1, that means C has to be smaller than D. Okay, this is enough, or smaller than or equal to D. This is enough to say that D is the greatest common divisor, because any other divisor that you choose is bounded by D. Okay, so that's all. That is the reason why it's enough to just select the minimum power when you compute the GCD, if you know the prime factors, of course. Okay, so all you have to do is use the prime factors and go through each prime factor and check whether the corresponding prime factor is present there. If it is not there, you can ignore it because you're multiplying it by 1 anyways. Otherwise, you just select the minimum power. If, say, P2 is present in both places, you just compute the minimum of A2 and B2. That will be part of your D. Okay, that's all. So we have proved a general theorem that if you know the prime factors of two numbers A and B, we can compute the GCD by just looking at the minimum of the corresponding exponent powers. Okay, that's all. Thank you very much for your attention.